So let's talk about numerical analysis. So why do we even care about numerical analysis? That is. So there's a lot of problems in math where numerical analysis historically has solved problems that we can't solve analytically. So what does it mean for a problem to be solved analytically? Basically what that indicates is that, if I wrote something down like 5x equals 10, then I can say that x equals 2. If I write down another thing, maybe x squared plus 6x plus 9 equals 0, then I can break this into x plus 3 and then an x plus 3 x plus 3 and a x plus 3, and that's equal to 0, so then I can say x equals 3, so there's repeated roots, right? So in these cases, I can find analytic solutions to the problem. Well, let's say I look at something like this. Let's say I look at x to the 76 plus x to the 50th plus 47 equals 0. Let's say I wanted to find solutions to this problem. It's a root finding problem, right? So, obviously this is an interesting math problem because there's a special result from a guy named Galois that talks about the analytic solution to finding root problems greater. Basically 5 is the magic number once you get to this guy, x to the 5th, to find analytical solutions to the root finding problem of polynomials. So, we might want to know for some reason what's the root to this polynomial. Can I find the root? I don't know. Obviously, we can't do it analytically because the great Galois said we couldn't, but we can start examining numerical techniques. So what do I mean by numerical techniques? So let's go back to the situation of 5x equals 10. Let's say something very trivial. So obviously we can say x is 2, but let's say we wanted to come up with a really good approximation, right? So, for the case of 5x equals 10, I can look at something like 5x minus 10 equals 0. So I could say something like, let's come up with a numerical algorithm. Let's say I don't know that, x equals 2 is the solution to this. Well, I could make a guess. I can guess. So if I have some xo, I can guess this to be equal to, let's say, 1. And then what I do is I plug it in, so I'll have 5 minus 10 equals 0. Well, that's going to be negative 5 equals 0. We obviously know that's not the case, but we know that because it's negative that we want to increase this xo. So we might say xo equals 3, let's say. So then we get 15x minus 10 equals 0. But then we get 5 equals 0. So basically we have sort of a sandwiching thing here. We know that the solution is between 1 and 3. Because if we go at 1, we get a negative number, and if we go at 3, we get a positive number. So, we can basically create an algorithm where we guess the xo, and we just keep on plugging it in, and we look at 5x minus 10, and we say that if 5x minus 10 is less than some tolerance, we say epsilon, that we know we're there. Because let's say I have epsilon be 0.001, let's say. So if I have x0 equal 1.999, if I look at this and plug it in, well, 5x0 minus 10, that's going to be small, right? So I know that I'm close to the solution of my problem, which is 2. So really what I'm trying to say here is this is really the foundation of numerical analysis. You know, we look at a problem. This is part 1. And 2, we say we don't know the solution. So what I say why we don't know the solution is, you know, if we write out the 5x equals 10, obviously problems are more difficult. You know, we don't know how to solve this problem. We do not know how to find this x in an analytic fashion. You know, obviously we know algebraically you can find it, but like let's say that we didn't know that you could find it. So we come up with methods. We come up methods to use basically the structure of our problem to figure out the x we need. Because once we figure out this x, we basically, the goal of numerical analysis, we're not really interested, well, the optimal goal is to find this x, but you know, the x is really our answer. We want to find the answer numerically to our problem. You know, with numerical methods, usually we don't get this x, we don't find the x. We rarely find the true x. I can talk more deeply in that, but yeah, in most general terms, if you find the specific x, there's really a reason why you were able to find that. Usually you can't nail it down. It's really a comment on convergence, but we can find this x star though. So what does that mean? So basically the idea of this x star is that if you look at the true answer, and right, we can like abstract this to vectors and whatnot, but you know, if you look at the magnitude of what you're trying to truly find and what you're, you know, what you think the answer is, and you look at the magnitude of that, and that's less than some small quantity, then you're getting there. And this is basically the idea of convergence. So that's saying that, let's say, with the previous example, I had a number line, right? And I started at 1, and I went to 3, and then let's say I was like oscillating back and forth. Our sweet spot's at 2, right? Well, I kept on guessing here, and then here, and then here. I'm basically coming closer. So eventually, what happens is that in terms of notation, we'd say that xn plus 1, you know, the next iterate minus xn is less than epsilon. Don't worry about this notation now, I'm just sort of saying it. So it's basically saying the last guess you used minus the current guess is less than epsilon, which is really indicating that you're getting close to your sweet spot that you want to get to. So overall, I really want to say that numerical analysis is super powerful. So really today, if we look at today versus the past, so really what was the problem with the past first? Well, a lot of these algorithms, they have convert, so it counts. You know, a lot of times when you look at this guy, xn plus 1 minus xn being less than a tolerance, a lot of times to get in this tolerance level where you're basically getting close to what you want as the answer, that takes a long time. So imagine that I had, for example, I had that xn plus 1, you know, my next guess is equal to xn minus f of xn over f prime of xn. So this is just an example for right now. So you can think about that we're interested in how fast a problem takes. So how long it takes until in the sequence we get here. So if we're writing it down, if I did this by hand every time, that's going to take a long time. Versus if I wrote this in a computer program, basically this thing will take seconds to execute. But based on the tolerance level, how close you want it to be to your answer, that still might take time. But in the past, maybe I want to have an epsilon equal to 1 times 10 to the negative 6, based on how fast convergence is happening. So that's really defined as how fast your approximate answer is getting to the true answer to your problem. That might take a long time by hand and even a long time by computer, but by hand it will take a long time to get there. But what's interesting is that really in terms of numerical analysis, well, okay, I won't write. So in terms of numerical analysis, because of the rise of computers, we can write programs with our numerical algorithm and we can get answers quick. And I say quick in quotes because, see, so there's really a discussion about this in the numerical analysis community. So some people are interested in, if we go back to the example 5x equals 10, they're interested in x equals 2. Whereas the numerical analysis person would be perfectly fine with this. Because even though this guy doesn't satisfy the equation, it's very close, even though this satisfies it. And the reason why, because for practical reasons, for more advanced problems, it's hard to find this solution. Versus with approximate solutions, we get close. We might not be there, but for our applications, this approximation is good enough. And this is really the power of numerical analysis today, because there are a lot of problems. I'll just sort of write one right now, just for funsies. We'll just write this. This is called heat equation. But for this problem, in terms of finding the analytical solution to it, it's a Fourier series, which, to really understand that on a deep theoretical level, is very advanced math. But to understand this, there's multiple things. I would probably write this as a finite differencing, but you could write this as a finite differencing, an implicit method, something like Crank-Nicolson. You don't need to know what that is, but you could write it as Crank-Nicolson, for example, and solve this numerically. So you could basically figure out the solution for heat equation without having to provide basically U equals, it's a Fourier series. I would write it because no one's probably interested right now, but you could write it as a Fourier series, but for more general problems, you can't even write a series solution for the solution of this PDE, so analytical methods are sort of important. So in closing, I guess I'll basically say that, especially in today's mathematics, if you're doing applied mathematics or basically applied mathematics, any sort of in-depth mathematical problems, it's all tied to numerical analysis, really, because a lot of problems can be numerically solved versus not solved analytically. So a lot of interesting things in numerical analysis, and there's tons of it, but really what I want to talk about overall is really, root finding, numerical derivatives, approximating derivatives numerically. The same thing with integration. The same thing with differential equations, linear algebra, PDEs, etc. Because what's interesting is, right, I'll save it for another video, but overall what's interesting is that with linear algebra specifically, analytically, if I have like a 3x3 matrix and I'm trying to solve AX equals B, I can do that analytically without a problem. Now, let's say, for example, I want to look at a 100,000 by 100,000 matrix. And I'm sure you're saying, why would I ever care about a 100 by 100,000 matrix? That seems very, very, very unneeded. Why do you care about that? Well, you care about it in this world, but what I'm trying to say is that when you get to 100,000 by 100,000, and you're trying to solve this system either by direct methods, which would be, if you're finding AX equals B, the direct method would be basically calculating the inverse and doing out this this matrix multiplication. But for iterative manners to solve this system, you need a computer because computers are very fast. So really, numerical analysis, at least in its current state, it counts if you're a theoretical person or applied person, but regardless, you're basically doing programming and you're coming up with manners how to take advantage of your problem in order to find numerical solutions for it. And there's tons of theory. And lastly, I'll just say nonlinear equations because this is very basically linear algebra is related to linear PDEs, and nonlinear solving nonlinear problems are related to nonlinear PDEs. But I'll just leave that there for right now. I just really wanted to talk about a general thing about numerical analysis. So I will see you next.